Okay. Do you know the this notation or thing?
Oh my god.
Okay. So we talk about the running time of the algorithms. ฟังนิดนึงครับ when we talk about the running time of the algorithms, this is the notation that we use. Okay. This O means that the running time function. So we want to quantify the amount of times that the algorithm runs. So the O thing, this O is called big O because it's a big O. You learn about it formally next semester when you take algorithm class. But it basically roughly say that the running time is proportional to this function. At most proportional to this function. This will be the upper bound. So the running time will not be larger than this. Okay? And then it will be proportional to this number. So it's gonna be mean x and y. So if x and y is like 1,000-digit numbers, okay, this will be like astronomical. This will be really slow, extremely slow. Okay. But how fast is Euclid? Euclid has to be faster, right? Somehow. So let me try to write a code that of the Euclid algorithms and try to perform it with some really large number. Okay. I'll do that after the break. I'll write the code after the break so to show you the actual speed of the algorithms. But let's try to analyze the running time of Euclid. Okay. So the number you try when you talk about the running time of the algorithms, when you want to say the algorithm run efficiently or run fast or slow, you need some way to, especially when you want to say that the algorithm run fast, you need some way to say that the algorithm makes some progress. It does something, okay? So with the numbers at your hands, when can we say that the algorithm stops? The algorithm stops when one of the number is 1, right? So if one of the number is 1, the loop will definitely stop. Okay? The recursion will stop when y is 1, for sure. Okay? Because any number mod 1 is going to be 0. So the algorithm stops when y is 1. So this is like termination condition. But how fast can we reach 1? How fast can we reach 1? If you look at the numbers in your exercise, do they decrease quickly?
Yes.
It decreases really quickly, right? So one way you want to say that the algorithm runs really fast, you want to be able to say that the numbers in the input after you make some recursive call decrease really quickly. Okay? If it decreases really quickly, then we're done. It's gonna stop really quickly because it make a lot of progress. It make progress really quickly. Okay? But before we do that, let's try to be a bit conservative. Let's try to show that it stops first. Okay? Don't think about how fast it stops. Let's make sure that it terminates. Okay? So how can we argue that Euclid terminates? When you call Euclid, you don't know the value of x and y. As we know that it's non-negative, it's positive. We don't know the value of x and y, right? So if it enters into these conditions, then it stops. So we don't have to worry about that. But if it doesn't stop, it makes this recursive call. Can we always say that the numbers, like the first argument, will decrease? We always decrease. Can we say that? Will the first argument of Euclid function always decrease? Sorry, no. If x is less than y, then after the first call, y will become x, right? So the first argument increase. Okay? But this only happened once. When you call Euclid, the first time you call Euclid, the user will call the function, right? So you have no control over the arguments. You have no control over x and y that is passed to Euclid. But after that, Euclid call itself. Okay, now we know exactly what are the value of x and y. So in the first round, x may be less than y. If x is less than y, after one round, x is going to be larger than y. Okay, and then now let's look at the code. If x is larger than y, when it calls itself, the first argument decrease. Right? So if x is larger than y, then when you call itself, the first argument decrease. Right? Why is that? Because we know that x is larger than y. So previously you call Euclid x, right? Second time you call Euclid y, so the first argument decreased because we know that x is less than y. But if what else do we need to know? We know that if x is greater than y, then when you make a recursive call here, the first argument is y, the second argument is x mod y. Okay? What can we say about x mod y and y? Is x mod y always less than y? Is x mod y always less than y? It's a remainder, right? So the remainder has to be from 0 to y minus 1, right? So it's got to be less than y. So after the first time, so if x is larger than y, first argument decrease, and also the second argument less than first argument. So this condition always hold. So if the first argument is larger than the second argument, okay, every time you make a recursive call, the first argument in the recursive call will always be larger than the second argument. Okay, so that means if the first argument is larger than the second argument, the first argument in the recursive call always decrease. So at some point it has to reach 1, and then your algorithm will stop. Okay, so this proof, except the first round, the first call, if x is less than y, then it's switch. Then that's it. This is the only time when x is less than y. Okay, it can be in the first call. But after that, x is larger than y, and then x always decrease. This means the algorithm terminates. Okay, but we cannot say, with this argument we cannot say anything about how quickly it terminates. But we know that it eventually terminates. Okay, so from this we can conclude that Euclid terminates. Okay, but we have no idea if it terminates really quickly or not. Okay, to say that it terminates really quickly, we need to make sure that the first argument not only decrease, but it has to decrease really fast. Okay, so we need to not only say that it decreased, but we want to say it decreased really fast. If you look at the result from your practice, you can see that is it decreased really fast?
Yeah.
Yeah, it decreased pretty fast, right? But can we prove that? That's the whole point. Okay? You can try some numbers and you see, oh, it decreased really fast, but it might not be always the case. Okay? As mathematicians, which we are not, but mathematicians need to prove it. Okay? We are not mathematicians, but we have to prove it as well because we are taking a math class. Sorry. Okay? But is it possible that the first number does not decrease a lot? So let me try to quantify. When I say that the first number decreased a lot, I want to be able to say like it decreased by a factor of 2. Okay? So like it's like divide by 2. It goes to half. If it goes to half, then every time the numbers like halves, it's like the number of bits that you need decrease by 1. So that's the idea. So I want to be able to say that, okay, this many, the first argument decreased really quickly, like it decreased by a factor of 2 every time. If that happens, then I'm really happy, okay? But it might not be, okay? So let me show you how, when it does not happens. So this is another example. But it might be the case that the first number does not decrease really quickly. Okay? So let's say when you call Euclid xy, right? It call itself, it call Euclid y and then x mod y. Okay? When can we say that the first number decreased by a factor of 2? So when y is less than x over 2, right? So if y is less than x over 2, then I know that the first argument decreased by a factor of 2. This is like stupid assumption. It might not be true because you can just call Euclid. Okay, if you call this Euclid, then after the recursive call, you will call Euclid, right? So it doesn't really decrease. It decreased by just not a factor of 2. It decreased by 7, and this is the case that I really hate because I want the first number to decrease a lot, right? But it doesn't. It just stay there, right? But the only way, the first condition that I can ensure that the first argument decrease is like when, so if y is less than or equal to x over 2, if that's the case, then I know that the first argument decreased by a factor of 2. Okay? We halfway done. So now we need to think about what happens if the first number is not less than x over 2. Okay? Like for example in this case. So in this case, what would happen? What is the recursive call that I made? Then I do this, right? So when I call Euclid, so this is my x and my y, right? So I put y here. And this, what is this number? This number is x mod y, right? What is it? What is x mod y in this case? When x is 1, 2, 3, 4, 5, 6, 7 and y is 1, 2, 3, 4, 5, 6, 0, what is x mod y? 7, right? 7. Is it small? It's small. So if the first argument doesn't decrease that much, I want to be able to say like this will be small, okay? And then the next time I call Euclid, what happened? The next time I call Euclid, this number will be the first argument, right? And you have something here. So we start from this and we move down to this. So after two recursive calls, I want to be able to say that if y is less than x over 2, then one recursive call, the first argument decreased by a factor of 2. Otherwise, after two recursive calls, the first argument decreased by a factor of 2 as well, right? So this gives you some example, okay? But why is that true? So the running time of Euclid. So, okay, there are two things that we need to talk about when we want to talk about algorithms. The first is correctness. Is the algorithm correct? We haven't talked about it at all, right? We assume that Euclid will return you the GCD. We keep talking about the running times, but that's not the point. The algorithm has to be correct first, but we'll talk about that later. Okay? Now we are worrying about the running time. Okay? So we want to be able to say that the Euclid algorithm run correctly and also the running time is good. Okay? The first will be easy because we almost proved it last time. We prove some property relating to this like last time. So we'll come back to talk to it. But we also need to talk about the running time. Okay? So let's look at the running time first. This is like in the wrong order. Okay? So when you think about the algorithms, the correctness comes first. You have to make sure that the algorithm is correct, and then you start to worry about the running time. Okay, but now we do it in the opposite ways because we are in a we keep talking about running time, right? Because that's the point. So but I should remind you again that the correctness comes first, but not today. Okay. All right. So let's look at the running time. So this is like what? Okay. So when y is less than half of x, the recursive calls the first argument decreased by half. Okay, this is what we had. Okay. So if y is less than x over 2, right? Otherwise, if y is larger than x over 2, you call Euclid xy and it's called Euclid y x mod y. Right? But what exactly is x mod y? Okay, what exactly is x mod y? So if you keep following this call, right? So it will look like pretty bad. Okay, so y become the first argument, and x mod y become the first argument here. Okay, so we basically want to compare x and x mod y. Okay, when y is larger than half of x. So let's look at the pictures. So this is x, and this is y. So how long is y? Can y be this much? We know that y is larger than x over 2. So x over 2 is here. So y has to be like this. Okay. Now, if y is larger than x over 2, what is x mod y? How many times can y divide x? 1. Okay? Because y is like larger than half of x. So when you divide x with y, the result will be 1. Okay? And the remainder will be, what is the remainder? The remainder will be this part. Okay? So how large is the remainder? So in this case, if y is really large, x mod y is going to be equals x minus y. Because y is larger than half of x, so x mod y is x minus y. And it's less than x over 2. Why is that? You can see the pictures. If y is larger than x mod y will be x minus y, but y is larger than x over 2. So what is left is going to be less than x over 2. Okay? So in that case, we know that this is like, wow, this is x mod y is less than x over 2. And this is what we want. When we want to talk about the running time, we want to make sure that the first argument decreases really quickly. Okay? The first argument decreases really quickly. There are two ways that the first argument decreases really quickly. The first is when y is small. If y is less than half of x, after one recursive call, the first argument decreases by a half. If that's not the case, then after two recursive calls, the first argument decreases by half. Okay? So either after one or two recursive calls, the first argument decreases by half. So it will decrease by half really quickly. That's why the algorithm works efficiently. Okay? So that's the idea. Okay, any questions? So when we do the analysis mathematically, we can say that so how many times until the first argument goes to 1? So the first argument decreases by a factor of 2 for at most log x of time. Why is that? So if you have a number and you divide it by 2, how many times you can divide? How many times can you divide a number by 2? It's the log of that number. Log base 2. Okay. So log is like when you talk about log, right? Log base 10 is like how many times you can divide numbers by 10, as long as it's larger than 1, right? So log base 2 is like how many times can you divide the number by 2? So The first argument can be decreased by a factor of 2 for log x of time. So the running time will be the log of x plus log of y, depending on like the larger number. So instead of, so if you compare this to the division only algorithms that we have, it's going to be min x, y, right? So it's going to be the value of x and y, but this will be log. So the log will be like much faster, extremely faster. Okay? So this is why the Euclid algorithm like run really fast. And it's a polynomial time algorithms. And this is like the basis of all the prime checking algorithms. And everything you do with like number theories, like RSA, stuff like that, will depends on this kind of like running time. Okay? Alright, so let me give you a 10 minutes break.